Hello, and welcome to the third video of my project showcase series. Today I'll be diving into a high-performance implied volatility calculator I've developed. This C++ program is designed to efficiently calculate implied volatilities for a large number of options contracts concurrently, with a specific focus on meme stocks. Now, you might be wondering, why meme stocks? Well, the rationale behind this project is quite interesting. I believe that meme stocks, due to their nature, have less institutional trading. This potentially leaves more alpha on the table for less sophisticated investors. Currently, I'm investigating the feasibility of various options trading strategies on GameStop, with plans to extend this to other meme stocks in the future. It's important to note that this program isn't based on a belief in the long-term performance of these underlying stocks. Instead, it is aimed at potentially profiting from the rampant speculation that often surrounds these assets. This implied volatility calculator is just one piece of a larger ecosystem that I'm developing to explore these opportunities. Let's break down the key components of this program and see how it all comes together. At the heart of my program's efficiency is the thread pool class. This class manages a pool of worker threads, allowing for concurrent execution of tasks. Here's how it works. The constructor creates a specified number of worker threads. Each thread continuously waits for tasks to be added to a queue. When a task is added, a thread picks it up and executes it. The enqueue method allows us to add tasks to the queue and get a future for the result. The advantage of using a thread pool is that threads are persistent, meaning they persist between batches. This decreases the computational overhead that comes with standard threading, as there is no need to spawn subsequent threads once the original ones have been created. This multi-threading approach is crucial for my program's performance, especially when dealing with large datasets of options contracts. Now, let's dive into the binomial tree American option function, which is a crucial component of my program. This function implements the binomial tree model to price American options, and there is a good reason why I chose this method over others. The binomial tree model is particularly well suited for pricing American options for a number of reasons. Number 1. Early exercise capability. Unlike European options, which can only be exercised at expiration, American options can be exercised at any time before expiration. The binomial tree model allows us to account for this early exercise possibility at each node of the tree. Number 2. Discrete time steps. The model breaks down the time to expiration into discrete steps. At each step, we calculate the possible values of the underlying asset and the corresponding option values. This discrete nature allows us to check for early exercise opportunities at each time step. Number 3. Flexibility. The binomial model can handle various types of options and complex payoff structures, making it versatile for different market conditions and option strategies. Number 4. Convergence to Black-Scholes. As we increase the number of time steps, the binomial model converges to the Black-Scholes model for European options. This gives us confidence in its accuracy while still maintaining the ability to handle American options. Number 5. Intuitive nature. The binomial model is based on a simple concept of up and down movements in the underlying asset price, making it more intuitive and easier to understand and explain than some other models. Now, you might be wondering, why not use the Black-Scholes-Merton model, which is often considered the gold standard? Well, while Black-Scholes is indeed excellent for European options, it falls short when it comes to American options. The Black-Scholes model assumes that options can only be exercised at expiration, which isn't true for American options. In my case, dealing with meme stocks, the ability to accurately price American options is crucial. These stocks often experience high volatility and unusual market conditions, making the early exercise feature of American options potentially more valuable. Here's how my binomial tree implementation works. Number 1, we start by calculating the up and down factors for the stock price movements based on the volatility and time step. Number 2, we then build the tree from the current stock price to the expiration date, calculating the possible stock prices at each node. Number 3, at expiration, we calculate the option payoff for each possible stock price. Number 4, we then work backwards through the tree at each time step, calculating the option value as the discounted expected value of the future nodes. Number 5, crucially, at each time step, we also check if early exercise would be optimal, taking the maximum of the calculated value and the early exercise value. This method, while more computationally intensive than Black-Scholes, provides us with a much more accurate pricing model for American options we're dealing with in the context of meme stocks. The heart of my program is the implied volatility function. This function uses Brent's method to find the implied volatility. Let's dive deeper into how this works and why we chose Brent's method. Brent's method is a root-finding algorithm that combines 3 powerful techniques: the bisection method, the secant method, and inverse quadratic interpolation. Here's why it's particularly well suited for my implied volatility calculations. Number 1, reliability. Brent's method is guaranteed to converge as long as the root is bracketed. This is crucial for us because we need a method that will consistently find the implied volatility, even in unusual market conditions that are common with meme stocks. Number 2, efficiency. While it's not always the fastest method, Brent's method offers a good balance between reliability and speed. It typically converges faster than the bisection method and is more stable than the Newton-Raphson method, which is another popular choice for implied volatility calculations. Number 3, no derivatives required. Unlike Newton-Raphson, Brent's method doesn't require us to calculate derivatives of my pricing function. This is advantageous because calculating these derivatives can be computationally intensive and prone to numerical instability. Here's how we implement Brent's method in my implied volatility function. Step 1. We define a function f that calculates the difference between the market price of the option and the theoretical price calculated in my binomial tree model for a given volatility. Step 2. We start by bracketing the root. We choose an initial interval, AB, where we believe the true implied volatility lies. If FA and FB have the same sign, we expand the interval until they have opposite signs. Step 3. We then enter the main loop of Brent's method. We keep track of 3 points, A, B, and C. Point C is the most recent estimate of the root. We calculate the next estimate using either the secant method, inverse quadratic interpolation, or bisection, depending on which is expected to give the best result. We update the bracket and continue until we reach the desired tolerance or maximum number of iterations. Step 4. Throughout this process, we handle various edge cases. If the root can't be bracketed initially, we return a special value to indicate this. If we reach the maximum number of iterations without converging, we return another special value. We also handle cases where the calculated implied volatility is not a number or infinite. This robust approach allows us to calculate implied volatilities even for complex or unusual option contracts, which is particularly useful when dealing with meme stocks where unusual market conditions are not uncommon. By using Brent's method, we ensure that my implied volatility calculations are as reliable and efficient as possible, even when dealing with the high volatility and unpredictable nature of meme stocks. The last function I'm going to cover is the calculate implied volatilities function. This function brings everything together and works using the following steps. Step 1. It reads the input data and sets up the thread pool. Step 2. The options are processed in batches for efficiency. Step 3. Each option's implied volatility is calculated concurrently using the thread pool. Step 4. The progress is reported in real time, including the calculations per second and the estimated time remaining. Step 5. Various statistics are tracked, such as NaN counts and root bracketing issues. Step 6. And then the results are written to the output in a CSV file. The function is designed to handle large datasets efficiently, making it suitable for analyzing entire option chains or even multiple stocks simultaneously. And there you have it. This implied volatility calculator is a powerful tool for analyzing options on meme stocks. By leveraging multi-threading, efficient numerical methods like the binomial tree model and Brent's method, it can process large amounts of data quickly and accurately. Remember, this tool is just one part of a larger strategy. While it can provide valuable insights into market dynamics and potential opportunities, it's important to use it as part of a comprehensive approach to trading and risk management. I hope you find this overview helpful, and if you're interested in options trading, particularly in volatile or speculative markets, tools like this can be invaluable. As always, trade responsibly and never risk more than you can afford to lose. Thanks for watching.